Hi everyone, my name is Judy Hoffman. I'm a postdoc at UC Berkeley and soon to be an assistant professor at Georgia Tech as well. So today I'm going to talk to you a bit about learning to be robust to changes in your visual environment. So all of us know that the ImageNet challenge is one of these huge performance boosts that you've seen over time. In general, especially since the resurgence in the use of deep models and getting bigger and bigger models, faster and faster GPUs, we've been able to train these really large networks that are able to perform very well at test time on the ImageNet challenge. But then you take that same big ResNet model and you try to recognize this dog in this video, and what you find is this dog is completely unknown. And it's not like it's confused with a similar animal. It just changes from frame to frame what would be the prediction from that same model that used to be able to recognize dogs in the ImageNet dataset. So this is a phenomenon that's been observed over and over again. And in the case of this particular shift from ImageNet to this video, what's happening here is there's a shift in terms of the capture bias of these two datasets. So in ImageNet, what we have is a large collection of images that were scraped from social media sharing sites. So things like a lot of Flickr images. And it turns out that the type of images that people like to share with one another are very inherently biased. So people want to share images that look visually appealing. So let's say you're trying to recognize dogs. Well, you're probably going to share a photo of a dog that has its face visible, because that's more interesting to you. You're probably, before you upload an image to a site that you want to share with your friends, you're probably going to take care to make sure that this image is the best in a couple of images. And what does that mean? That means that it's roughly in the center of the frame. It has nice resolution. It has good lighting conditions. All of these are kind of classical things that make a good photo in photography. And so when you take a model that's trained on images like this and then try to recognize the dog in a video, you now have to deal with all sorts of other biases that come out of what was interesting to share in the video medium, such as lower resolution, motion blur, and a larger variety of poses than you saw in the still image database. And this causes a huge degradation in performance for our models. So we also see that even if you're not talking about different data sets, you might have a large difference in terms of performance. So let's say we have a self-driving car, and the goal here is to be able to understand the street scene. So that might mean being able to recognize the road, the pedestrians, and the cars. So we can take a model that was trained on one collection of data, and it seems to work well in that scenario. And then we want to ask, how well does it perform at recognizing street scenes when there's snow present? Well, it turns out that if you were to train a model and you somehow only saw sunny weather conditions, and now you want to recognize it in snow, you get all types of confusions. So in this case, for this particular image where we trained on fall weather condition and we're trying to evaluate in the winter, we found that the snow-covered street was confused with buildings. So the question that a lot of this work that I'm presenting is going to ask is really, how can we learn to generalize a model that was trained under one sort of bias condition and reuse it or adapt it in a new setting without asking people to intervene and label lots and lots of new images? So this problem has been classically formulated under the notion of domain adaptation. In domain adaptation, what you have is access to a large labeled source data set. So in the case of visual recognition, this might be the ImageNet data set, or it might be a collection of product images taken from a product warehouse, or it might be simulated imagery. But in all of these cases, the key here is that you have access to lots and lots of labeled data in one regime, and so we can use standard supervised learning techniques here in order to perform a model or produce a model that performs well on this data. Now, of course, the problem arises when the data that you would like to recognize at test time is not drawn from the same distribution. So this might be the fact that you now want to recognize in videos instead of still images. Or you'd like to recognize those same products but in the wild. Or you'd like to use your simulated model in order to recognize those same street scenes in the real world. So what we're going to talk about today is how can we take these models that were trained in a supervised fashion in one setting and adapt them for use in a new setting without access to labels. So kind of the standard formulation, maybe 5+ years ago for domain adaptation in the computer vision community, is to have access to a large labeled source data set. Shown here is this product image, and then an unlabeled target data set. You'd then have some sort of hand-designed representation, and you could use that representation to extract useful features from these images that you could then use to train some semantic classifier, in this case, bottles and mugs. And the problem of adaptation then arose exactly when there was a distribution mismatch in this feature space between the source and the target data. So the goal here is to be able to learn a new representation which doesn't succumb to this same problem and instead is invariant to the differences between the source and the target data. And so instead of having this fixed representation, of course, as we all know, we now learn these deep representations. But the really important thing about having a deep representation in this case is the fact that it is not fixed, and you can actually use this discrepancy between the two distributions as a supervisory signal in order to train these representations. And so to do that, we're going to explicitly modify the representations so as to minimize the discrepancy between the source and the target distributions. So some of the earlier work that did this looked at really simple measures of statistical difference, such as mean differences or other higher order statistical alignment techniques. And what I'm going to talk about today is how can you do this using what's called the DH discrepancy. And this is pretty interesting to us because it has a nice connection to some of the theoretical literature in domain adaptation. In particular, what it tells us is that if you minimize this type of discrepancy, you get a bound on the error that you would expect in your target domain. So really briefly, this notion of discrepancy is simply just asking how large is the difference in terms of the difference between your source and your probability space under any given partition of your space. And once you have that notion, you can now derive a probabilistic upper bound on your target. And kind of importantly, this upper bound is in terms of two key functions. The first is your source error. And the key about that is your source data set has a lot of labels. So this means you can use supervised learning to drive down the error in your source. And then it's also in terms of this notion of discrepancy. And this is something that we maybe can modify inside of our learning procedure in order to minimize. And then the last term has to do with the best possible joint model. So, of course, you can't actually compute discrepancy because we don't actually know the full distributions. But what you can do is you can take samples from the source and samples from the target, and to kind of skip all of the details, what you find is that if you would like an empirical approximation for discrepancy, it can be computed exactly in terms of what's called a domain classifier. So kind of the important takeaway from this is that we have this distributional distance notion called discrepancy. And it's an important notion because it gives us some sort of a function of the upper bound that we should expect in our desired test set. And you can compute this discrepancy by looking at the error of the domain classifier. So in this case, a domain classifier is simply a classifier whose job is to be able to predict, did this image come from my source or from my target? And this is something that we're very capable of training, and you don't need semantic labels in the target in order to compute this. So we're going to minimize discrepancy by first estimating it by training this domain classifier. And then we're going to update the underlying representation so as to confuse this classifier using an adversarial loss. So to understand how that optimization works in a little bit more detail, we can look at an example. Here we have source, images, and labels. And because we have a lot of labels here, we can, of course, learn a representation, which is useful for classifying this data. And so these points will fall somewhere in space such that they're well separated. But then the problem of adaptation arises when you try to view this new collection of data under the same source representation. And in particular, if there is this discrepancy between the red distribution and the blue distribution, then we know that the target error is upper bounded by a larger quantity. And so we'd like to minimize this discrepancy. And so the way we're going to do that is we're going to iterate between estimating it by training a classifier to be able to distinguish between these product-like images and the real-world images of the products. And then we're going to update the underlying representation, meaning where these points fall on the screen, according to confusing this domain classifier. So once we do that, these points will move in such a way that now that domain classifier performs poorly at distinguishing between the red points and the blue points. And now, in this new updated representation space, we can again learn a semantic classifier to recognize the bottles and mugs using the red labeled data, and it'll perform better on the blue unlabeled data. Of course, this is iterated in high dimensions until there's no longer a domain classifier that can distinguish the product images and the real-world images. So altogether, this gives us what we call domain adversarial learning. And as I presented it so far, it's really focusing on learning an invariant feature space by minimizing discrepancy on this representation. But you could, of course, equivalently think about it as directly minimizing discrepancy in image space. And if you do that, it starts to sound a lot like generative adversarial nets, or at least conditional GANs. And so to understand some of the differences between image level domain adaptation and what people might do in the unsupervised feature learning with GANs, we're going to look at a small example for digit recognition. So in this example, what we have are a labeled source data set from Google Street View house numbers, and our unlabeled data set where we'd eventually like to recognize the data is this MNIST data set. So a conditional GAN would take as input a Google Street View image, learn to map it into another image, and supervised by this loss that says it should, in terms of style or overall statistics, match the image from the true MNIST digit data set. And people have found that you have all types of problems with training these things and different mode collapse. And so others have introduced further sort of regularized versions, such as the CycleGAN work, which adds this cycle consistency term, which basically says, okay, once I've mapped it and supervised this first mapping of the image according to a stylization loss, well, now let me make sure that I can also take this image, remap it back into the source domain, and it should be remapped in such a way that you minimize the L1 loss between the original source image and my double stylized image. And this is supposed to really encode some sort of low-level structural consistency, which should help the training avoid some mode collapse. But what I'm going to show you next is that because these methods were developed for purely unsupervised feature learning, there's no connection here necessarily to ground truth semantics that we care about for these particular visual recognition tasks. In this case, recognizing that this is a 3. And so what you get is some really peculiar failure cases. And here are some examples of source images from Google Street View. And here's the example stylized image to look like MNIST. And it has the correct style. And perhaps more surprisingly, you take that image and restylize it to look like Google Street View, and you find that it also has a pretty good reconstruction of the original image. But you may have noticed that it has completely wrong semantics in between. So this is not going to be very useful for us for doing domain adaptation. Because in domain adaptation, our goal at the image level would be to map our original image into the target domain and then use that image in order to train a supervised model. But if we do that here, well, now we're going to learn the completely wrong semantics. And it was not a systematic shift. These kind of label flippings just happened all over. But fortunately, since we are doing domain adaptation, we have access to a lot of labels in our source data set, meaning Google Street View. And so we can use that in order to produce an extra semantic consistency loss. In this case, what the loss does is we take our object classifier that was trained on our source data set, and we simply require that before and after we do this image transfer, we produce the same semantic label. So once we do that, we can now take our Google Street View images and map them to look like MNIST and make sure that they retain the correct semantics. Of course, these mappings won't be perfect replicas of the MNIST digits, and so we can then further combine this with our representation space alignment to take us just that further in terms of aligning the discrepancy of the original source and the target data. So once we do that, we can look at the recognition performance on this MNIST data set. And if you were to just train on Google Street View and then evaluate on MNIST, you get about 67% accuracy. A bunch of other people, I'm sure you'll see more as this conference goes on, have worked on these kind of unsupervised domain adaptation techniques using variants of feature alignment and image space alignment. And a couple of them are shown here. This particular work gets you up to 90%. And for reference, of course, probably many of you know, the MNIST data set is relatively solved in the supervised learning context. But kind of the key takeaway from this is simply that without any labels in the MNIST data set, you can go from 67 up to 90% accuracy just by taking into account both this image space and feature space alignment between the Street View and the MNIST digits. But of course, this is just digits, and perhaps not the most interesting of examples. And so another example that we've looked at is being able to adapt for semantic segmentation in driving scenes. So semantic segmentation, of course, is being able to produce a pixel level output that specifies the semantics. In this case, things like cars and road. And this kind of data is really expensive to annotate. In a data set we're collecting at Berkeley, it was $10 to $12 per image. So even if you want to take the route of collecting lots and lots of data and labeling it, which you definitely should for self-driving applications, it's still a very expensive and tedious process. And more concerning is the fact that there are all kinds of variations that you might have to deal with in the self-driving setting. So even if you've collected a large data set, you're unlikely to have covered all weather variations, all lighting conditions. If you change your cars, if you change your sensors, all of these kind of small differences can make a big impact in terms of your overall performance. So to study this problem, we're going to look at 3 different adaptation settings. And these settings are chosen just because they make some semantic sense to us. But in general, as I said, you could find all kinds of small differences just from one collection to another because of lighting changes or because of sensor changes. So the first setting we're going to look at is cross-city adaptation. So in this case, we have a labeled source data set, which is cityscapes. This is a collection of images taken around German cities. And then as our test time unlabeled data set, we have driving scenes around San Francisco area. Now the differences between these 2 collections of data are things like the fact that the German streets tend to have less wide lanes than the San Francisco streets. You see a different variety of cars. In San Francisco, you see more tunnels. The street signs look different between these 2 places. So I'm just going to show you one example here of a test time image in the San Francisco data set. And I'm going to zoom in on part of this image that looks at a concrete building. So before adaptation, you confuse this concrete building with things like sidewalk and road, which makes some sense. And then after adaptation, you're able to start recognizing this as the building that it is. There's another example where you could use this sort of domain adversarial technique. We're going to look at cross-weather adaptation. So here, to study adapting across weather conditions, we're going to look at the Cynthia dataset, which is a synthetic dataset that renders street scenes under different weather conditions, so it's particularly conducive for this study. And we're going to consider training in the fall weather environment, and then trying to adapt for recognition in the winter weather. So we're going to start by doing image space adaptation. So here what we have is our fall image, and we're going to make sure that it looks more like a winter image. And after we do that, we get this output. So the basic differences to notice are that snow appears on the sidewalk and on the rooftops. And then we can further adapt in feature space, and then evaluate our performance on test time winter images. So here we have an example winter image in the ground truth. And before adaptation, this is the image I showed you before, you confuse the snowy road with buildings. And then after adaptation, you start to recognize the road. And again, this is without any annotations in the winter setting. And this is something we saw systematically, that the road and the sidewalks and things that were covered in snow saw a lot of improvement after this adaptation technique. As a final example, I'm going to show you adapting from simulated to real world. And in this case, for the simulated image, I'm going to use a data set called GTA, which offers us pretty realistic renderings of street scenes. And as our test time real world data set, we're going to use this cityscape German driving data set. So again, the first thing we're going to do is we're going to take our image from GTA and we're going to stylize it to look more like the cityscapes data set. So after we do that, we get this image. So the difference is here. GTA is emulating street scenes around Los Angeles, which happen to be much rougher looking, different potholes, non-smooth. And after adaptation, we get the nice, smooth German road. And the center line here is yellow. After adaptation, it turns to white. And then finally, I find it pretty amusing to note that the cityscapes driving data set was all collected on the same car, and that car always had the same hood ornament visible. And so that turns out to be a key detail that we learned to emulate. Okay, so you can take this sort of image space alignment technique and then further do feature space alignment on these transferred images in order to produce our final test time real-world adapted model. And when you do that, you can look at a few example images. So here we have the test time cityscapes image and the corresponding ground truth. Before adaptation, meaning just training and simulation and evaluating the real world, you have a whole lot of confusion. After adaptation, as I mentioned before, you start to recognize the street a lot more accurately. You also recognize certain key characteristics for the driving application, like a pedestrian and street signs. And again, this is something we systematically saw. The road gets much more visible, and small objects that are pretty critical, like street signs, are starting to become more observed. So we can look at overall mean IOU on this cityscapes data set. Again, this is without using any annotations in cityscapes. And what we can do is we can evaluate first how well does our simulated model perform on this data set. And then we can get around 21% mean IOU. And here, if we were to train inside the cityscapes data set with all of its labels with this particular model, just for reference, you could get 67 on this metric. And then what I'm showing in the middle are sort of an ablation of these two components of the model. So the model itself can get you up to 39. And if you were to perform either representation space or image space alone, you could get 31 and 37. So what this shows is that first, they're both kind of complementary in terms of what they offer in your adaptation solution. And another thing to notice is that in this case, when you're looking at mean IOU, it appears that image space alone is performing better than representation space alone. But this is kind of a little bit deceptive just to look at mean IOU, because now if we were to look at frequency-weighted mean IOU, this means take the same IOUs but weight them by the prevalence in terms of pixel space in the image. Now we see the opposite result. And this is that the representation space is outperforming image space alone. So why does this happen? The representation space is studying simply overall statistics in that representation. There's no low-level structural consistency to make sure that you don't wash out the results of small objects. And so it doesn't perform as well as adapting those things. So this is why representation space alone, if you were to look at just the road performance before and after adaptation, you almost recover supervised performance without any labels. So this occupies the bulk of the actual distribution that you're computing discrepancy between of these two data sets. And so this kind of leads us to maybe think about future things where if there's a particular class that's very important to you, you might consider different type of representation space alignment that's weighted by the classes. So altogether, this gives us domain adversarial learning. And again, it can be applied at the representation space, it can be applied to image space, or both together. And I showed it to you both on the digit example to explain how it was different from GANs, and also on the semantic segmentation for driving scenes example. In the remaining minutes of this talk, what I want to talk about are something a little bit going forward, which is that everything I've talked about so far has really focused on this idea that you have access to a source data set and a target data set. And that, in general, is a pretty static assumption. And if we really look at the data that you might observe for this driving application, let's say, what you see is that the data, even from a particular drive, is not really static. It's not really one domain necessarily, but more of a continuum of domains over time. And so it's maybe important to consider this idea of how well can you keep adapting over time. So a few years ago, we started thinking about this problem, and in context of that, we collected a data set that really pretty clearly shows you this problem of continuous adaptation, or in other words, a domain that's sort of evolving over time. So this is a data set that is a collection of images taken from a traffic camera pointing at an intersection outside Lake Tahoe. And the camera doesn't move. The only things that really change in the scene are cars come and go. And then there's going to be a lot of variation in the scene itself that we'll call this domain shift over time. So first we start in the morning, and then as the day progresses, you start to see large cast shadows come over the scene. It changes into nighttime and the sensor changes. At some point during the night, a snowstorm hits, and you start to see that the visual appearance of this same static road is changing pretty dramatically. So at that time that we produced that data set, we combined it together with an algorithm, which I'm not going to go into, but it basically looked at walking along the manifold, or iteratively estimating where you are on this subspace manifold, and then using a geodesic flow kernel at that time to do the transfer between your labeled data set and your current data set. But if we were to try to think about this problem in the context of the domain adversarial learning that I was showing today, well, one thing you could do is you could think about this original hour of training in the sunny weather as being your source. And now just place all of your future images as time progresses into this network and optimize it with domain adversarial learning. But if you do that, you're going to run into all kinds of different important problems. The first is that you really want a model that is generalizable. And what I mean by that is we don't just want a model that can be responsive to what it sees right now at the expense of forgetting everything it used to know. We want a model that's able to capture all variety that you might see, and that includes retaining knowledge from prior experiences. We also want a model that can be learned to adapt quickly or in a sample-efficient way. So that means that I don't want to have to wait until it's been snowing for 3 hours before I start adapting to snow. And then finally, we need a model that's going to be scalable. And what I mean by that is that a lot of the solutions in learning without forgetting old experiences or different lifelong learning scenarios require you to either retain old copies of your models, which becomes infeasible over time as the domains change over and over, or retain all of your old examples, infeasible. So what we've been working on, and this is just some preliminary work right now, is on a simple unsupervised adaptation technique that can be applied over time. And in particular, we're going to study applying it over time as there's a domain that kind of changes with a particular constancy over time. So the way that this model works right now is we have access to our large labeled source data set, and at time 0, we have access to some new data that's unlabeled, and this is our first target. And what we can do, of course, is perform our standard unsupervised adaptation between our source model and this target model. But then we want to make sure that we don't forget the old things. And so to do that, we're going to keep a very small subsample of our prior experiences. And we're going to use what we call a replay loss, which is something that's done quite frequently in the DeepRL literature. And in DeepRL, they have a pretty similar problem setup where your experiences come in a sequential and inherently correlated manner. And so in order to make sure that you don't overfit to what you're seeing right now, they'll do is they'll make sure to keep around old experiences that can be sampled at random, but basically make sure that the model is robust to all of its old experiences. And so we're going to do something similar here, and this will provide us with the model for this first time step. And then as time progresses, this model just continues. We again can adapt to this new data as it comes in. We again keep around a small subsample. And once we've done this, we now can evaluate our model both in terms of its performance at a particular time step, as well as how well it performs on past data. So to study this, we're going to just look at a really simple problem of MNIST rotating over time. So this means that we're going to consider having some labels for these upright digits, and then we want to evaluate performance as these digits rotate over time. So the first thing to evaluate would be how well can we adapt to these rotating digits. And so that's what's being shown here. This is an accuracy versus rotations. And this is just the instantaneous recognition performance. So at that time when you adapt to it, how well do you actually perform? And what we see is that the model is able to essentially retain full performance and effectively adapt to these different scenarios. And we also see that replay loss is irrelevant for how well you perform right now, which kind of makes some sense. But now we can ask, how well did you remember your old examples? And so what I'm being shown here is an average over all past rotations of your accuracy. And what we see is that when we include this replay loss, we retain a lot more of the performance than when we don't. And this, again, makes sense because without the replay loss, there's nothing to make sure that you don't forget old things. And in general, what you're actually learning with at a particular point in time would just be to adapt. And this replay is actually a tunable parameter. You can control the weighting between the two losses, both the adaptation loss and the replay loss. And what we see here is that as you weight the loss higher and higher, meaning weight your prior experiences as more and more important, you just find that the performance on the previous domains goes up and up, but it does start to hurt the current domain performance. Again, this is a pretty intuitive result. Okay, and as the last example, I just want to show some of the power of thinking about domain adaptation in this continuous context. So let's say that we have trained our model all the way through the digit rotations. So that means that we had source labels for 0, and then we applied our adaptation with replay to 45, 90, so on, all the way through 315. And then we want to evaluate performance just on the prior experience of 135, which is shown here. Well, if we just take our model that was trained on 0 and evaluate on 135, we can look at this confusion matrix and find that it just does horribly at recognizing on this shifted digit. And if we were to try adapting to all of the different rotations at once, you also perform fairly poorly, though improved over source alone. If you try adapting without the replay, then what you find is that you forget how to recognize this 135. And then finally, if you adapt with the replay, you're able to retain this performance and really nicely recognize these digits in 135. So to summarize this part about continuous adaptation, what I basically want to say is that the batch model alone doesn't always necessarily work. So here is an example from that traffic camera intersection where if we were to try training in this sunny weather condition and then immediately move to this complete snowstorm, that might be a very hard adaptation problem. But if we instead adapt smoothly over time, what we found is that we're able to retain performance over and over using these incremental adaptation techniques. And then combined with the replay loss, we're able to retain the old performance. And so that together gives us this kind of preliminary work towards continuous adaptation that I would love to see more people working on. And with that, I'm just going to take a moment to thank my collaborators who helped with this work and take any questions you might have.
We only have this mic over there. So if you have a question, please go to the middle. So thank you for your talk. I think it was very interesting. I really love your work. Please.
Hey, I got one question. So, how important is it that after the domain transfer, the images look actually visually like the target domain? Like, how is it correlated to the performance at the end? Is that critical? And you're saying basically you want to convert visually from one domain to the other domain, or do you think, oh, maybe there's something else the network can figure out which gives you equally good performance, or almost equal good performance, but doesn't have to look exactly like that domain?
Yeah, this is something I've looked at a bunch. So in general, what you're asking is essentially how important is what we perceive at this intermediate state? And to kind of think about that even at a little deeper level, one thing I'm really curious about and have been working on for some time is, do we even need to go all the way to the pixel space, or would even just Conv1 adaptation help us? And I think it's still an open question, but what I've observed is that, at least kind of anecdotally, when it looks more similar to the target images, it seems to perform better. But I don't think that means that there isn't an intermediate state that wouldn't look visually appealing to us, that would also give us strong performance improvement.
Okay, thanks.
Take this one. Great talk, thanks. I have a question. So, like most of the works you've showed, you have assumed that there's basically no label from the target domain, right? But sometimes spending $10,000 for labeling 1,000 images, that might be okay, right? So for instance, if you look at the performance on, so my question is, on cityscapes, performance is pretty high. So if you want to go beyond that performance, so let's say from 82 to 90% instance segmentation or semantic segmentation, do you see any hope that this domain adaptation, or is there any indicators that these domain adaptations techniques will get us there at some point?
Yeah, so this is more a question of, let's say, like generalization or few-shot learning. It can also be thought of as semi-supervised adaptation. They're all kind of very similar things. And we looked at that a bit. I've looked at it more in the context of task transfer, like can you learn a new task faster with fewer examples if you take into account that you've previously learned a different visual task. And that's definitely true. But I think it's probably an important question to know, can you improve upon fully supervised performance? I think to evaluate that, we need to move beyond smaller data sets because supervised learning works very, very well at remembering when you have a pretty homogeneous type data set, especially with fewer images and kind of, in the case of cityscapes, these structured scenes. And so if you want to kind of improve upon performance from outside of your domain, I think what you would need to do is start out with a pretty diverse domain and kind of evaluate as you incrementally learn more and more labels, can you improve your performance faster and faster?
Hi. I'm interested in how much does the model trained with domain adaptation perform on the source domain? Does it perform worse than the model trained on source only? And how much?
So the answer to that question will depend on the specifics of how you train your model. So there's two versions of this. One of them is where you're using the source representation as initialization for the target and as a kind of fixed supervisory signal. And in that case, you have an explicit source model that's kept around. And so obviously you haven't changed it, so it doesn't hurt performance. In the other situation, when you share a representation, so trying to learn a single generalizable model, you can see a slight drop in performance, but you're continually training with the source labeled supervisory signal. And so it's not going to drop very much because you still have that loss in there. And again, that will be a tunable parameter, how much you want to make sure that you remember the old things versus adapting to new things.
Thank you.
Yes.
We're getting to the beginning of the next section.
Yes.
So maybe take one super short question.
Okay, yeah, very short. Okay, thank you for the talk. So I'm very interested in the generated video from GTA to the cityscape Germany driving. So it looks very temporal consistency. So do you do any post-processing step to make sure it's consistency?
No, I mean, I think that maybe that's because also you're far away from it. If you look at it on the screen, there definitely are small flickering that happened. We didn't do any post-processing on that video. I think you definitely could. If you want to work on doing pixel adaptation really on videos, it makes a lot of sense to use temporal consistency. And there's probably newer adaptation methods you could come up with as well that use temporal consistency as another self-supervisory signal.
Okay, yeah, thank you.
Okay, thank you, Judy. Sorry to push, but we have a very tight time schedule. And we will now continue with the stereo.